Hello everyone, good morning. My name is Gaurav. I am from Exasky Labs, advised by Dr. Barbara Chapman. So, talking about edge computing, last year during this time, Zoom had announced like for its hybrid conference room, they will move most of the processing at the edge. And not only that, like apart from that, if you talk about IoT devices or autonomous vehicles, then healthcare, monitoring in healthcare system, or monitoring water levels for the agriculture, optimized agriculture everywhere, edge computing is ubiquitous. We can agree to that point. And also there has been a kind of like paradigm shift from cloud computing to more of hybrid computing or edge computing and edge computing. So the factors that are spreading this move is like edge computing has mainly low latency, improved bandwidth, low power consumption, and it is more secure. So these are the few factors that is bringing in a paradigm shift from cloud computing to edge computing. But I mean, it sounds good, but is it easy? Unfortunately, it is not. So there are like a lot many things that we face as challenges. For example, let's take very simple example. We have diversified hardware, backend devices. For example, we have CPUs, GPUs, and ASICs like FPGAs, microcontrollers, and so on. So let's assume like we are an application developer. We write a PyTorch code, and since this most of the applications are like DNN dominated, deep neural networks dominated. So, for example, I write a code in PyTorch and expect it to efficiently execute on a given hardware. And tomorrow, someone introduces a new hardware, a new microcontroller. Can I expect it? Can I expect it to execute efficiently on that also? May or may not be. So that's the challenge, and that's where my research comes in. So there are compilers being introduced, like we have TensorRT, TVM, TensorFlow Lite, and these are mainly designed to accelerate deep learning at edge. So these are quite flexible as well as efficient compilers, theoretically at least. So now, where does my research comes into picture is this. We started like a couple of years ago studying these compilers and what are the various optimizations that they have to offer. Then after that, we try to propose an algorithm where we can optimize the execution of DNN based on different compiler optimizations. So we will apply compiler optimization on the DNN in such a way the whole compiler time can be reduced, keeping the throughput intact, or in the best case, lower the latency. And we could achieve over 70% reduction in the compiler time for models like Word. So that was one achievement. And so from here, where should we move ahead? So now we are trying to come up with an engine or with a framework that can be extended to any of the given compilers, where it will extract the structural and statistical information from the graph. It will rewrite the graph in such a way that the number of nodes can be reduced to better apply the optimizations. And then it will extract the hardware characteristic, combine all these features. It need not be a machine learning or intelligent. I mean, it has to be an intelligent algorithm, need not be machine learning based, but a better novel methodology to optimize the execution of DNN on given any new hardware. So this is where we are heading towards, and that was all. Thank you.
At the edge, you must be worried about inference or people actually trying to do learning.
Oh yeah. So I mean, this is one because of time I couldn't speak about it. So mainly the main area is inference because most of the applications are inference driven. But recently, for example, Google and for the keyboard and all, they have also started kind of like in very rare cases online learning. So that is something, or else partial transfer learning. So that is one way where they are heading towards because the training data set is quite lesser in those domains. If it is huge, then that's a challenge because most of the applications are constrained. I mean, they are constrained under like compute availability or memory usage, energy, and power. So those are like quite parameters for us also, quite important parameters. So if we are saying we are optimizing, so these are the parameters that we are targeting. So if a user wants on a trade-off like power to optimize it or throughput, so that may vary depending on the application. For example, scientific application, high energy physics, accuracy is more important rather than
medical applications too. Yeah.
Exactly.
And are we seeing neuromorphic processes being deployed now, or is that still just research?
That's a research area. IBM, as far as I know, like there are a few good researchers working on that, and even industry is investing in that area. So one problem is that with neuromorphic is not problem. I would say it's a research area, probably open research area. Is sound signal to noise ratios. So they claim the latency has reduced, but then when we look into signal to noise ratio, that's still a challenge. And also the underlying hardware. So currently there are like we are almost crossed the end of Moore's law, and now we are coming with more crossbars or analog computing rather than digital. But then it has its own challenges, and that is a prerequisite kind of thing for a neuromorphic. So here, yeah, good question actually. So the main thing is about tensor operations. What are the operators being executed? So why the performance is getting a hit? Because that operator may not be supported on a given hardware, and then it will fall back on the possible, or like for example CPU. And in that case, there will be a lot of data movement or operation movement, and that's where the performance hit is really happening. So yes, machine learning, the operations are quite defined. It's more of mathematical. And in a previous talk, they talked about differential and all those things, algorithms. So that kind of thing that it is helping it, even DNN. But the major difference between both of these are like kind of operations being performed. So that is the main area.